marker metric to describe space-time on large scales and to describe how we make observations, what the luminosity distance means, and so forth. I have, I think, too much material to present on the blackboard in the hour and 15 minutes that I have, but there will be lecture notes available after the break that will allow you to fill in any of the gaps. Let's use the full board. Thermal history is important because there are many particle interactions throughout the history of the universe that have affected the composition and structure of the universe today and, of course, its expansion rate. Also, we look at particle species, photons, and so on to try and deduce events that happen in the early universe to test and go beyond our standard model. So it's important to understand the processes that took place. And for most of the history of the universe, the density of the cosmic plasma was low enough so that binary or two-body collisions predominated over three-body collisions. I'm not going to be talking about strongly interacting plasmas where many-body physics is needed. So at modest particle density, well after the QCD phase transition, binary collisions predominate. And I have two types. If I have two species A and B, they can either scatter elastically or the species can change, as, for example, occurs in annihilation or creation of particles. There are, of course, other cases. You can have excited states in the final products or in the initial products and so forth. I'm not going to go into too many details here. I've drawn the reaction pathways both ways because in chemical equilibrium, the lower interactions occur in balance, equal rates, forward and reverse interactions. And in kinetic equilibrium, the upper reactions occur at equal rates. So this drives kinetic equilibrium, which means you'll recall that the particle distribution functions have the thermal form depending on a temperature and a chemical potential. Reactions that change the products in equilibrium give you the law of mass action, which is relationships among the chemical potentials. And much of the interesting processes in astrophysics and in cosmology focus on conditions where these equilibria break down, as will happen at low densities. So let's make some estimates of when equilibrium might break down by looking at the rates for these reactions and comparing them with the Hubble expansion rate, which is the driver of cosmic evolution. As the universe expands and the plasma dilutes, if the reactions can keep up faster than the Hubble expansion rate, we have equilibrium, otherwise not. If I focus on species A and ask about the collision rates for that, call it gamma sub A, that's the number density of species B that it's colliding with times a cross-section times a relative velocity of the products, cross-section times flux. And if the particles are in thermal equilibrium described by some temperature and chemical potential, then I have a thermal average of this product, cross-section times relative velocity. That will just be a function of temperature and perhaps chemical potential for products A and B. Now, for abundant species relativistic species in kinetic equilibrium, n sub b is proportional to t cubed. We showed that last time. That's the limiting form of this distribution function integrated over volume. And then the sigma times V will be some function of temperature depending on the momentum dependence of the cross-section, on whether the plasma is relativistic or not. Here, by assuming this, I've kind of assumed that the plasma is relativistic so that this V would be the speed of light, characteristically. And I'm just going to write this as t to some power of alpha. It may or may not have that form depending on the interactions. And for most of the processes of interest that I'll be describing today, this alpha is positive, though, of course, for many important processes, it is not. For example, for Coulomb scattering of non-relativistic particles, the Rutherford scattering cross-section increases steeply with decreasing velocity, and this would give a negative exponent for alpha. So be careful to look at each process here. And what we want to do is now, to check equilibrium, compare this rate with the Hubble rate. And from last time, if the expansion is fast enough, I can neglect the spatial curvature, which I will do. I have 8/3 pi g times rho, and for the density of a plasma in the fairly early universe, we're working primarily in the radiation-dominated universe, where there are lots of photons and other relativistic particles possibly present. Then we have the number of relativistic degrees of freedom, t to the fourth, and I'll take that out, call it t squared. So that means if I take the ratio of this interaction rate to the Hubble rate is proportional to t to the power 3 minus 2, or 1, plus alpha. And for the typical processes that I'm concerned about today, this exponent is positive. So as the universe expands and the temperature decreases, the interaction rate decreases compared with the Hubble rate. And if it starts out faster than the Hubble rate, there will come a time when it becomes slower than the Hubble rate. And it comes of order 1 at either kinetic or the breaking of kinetic or chemical equilibrium. And those two different cases have names. For the breaking of kinetic equilibrium, it's called decoupling. And for the breaking of chemical equilibrium, it's called freeze-out. The freeze-out name is chosen because when the reactions of product A cease, changing its number, then the co-moving number density is frozen out. It's conserved. And we can look at this schematically. Well, let me not get ahead of myself. Let me consider a few important examples of this process, the freeze-out or the kinetic decoupling. I won't have time to do all of the relevant examples in the early universe, but I will outline a few that show the idea, and then I'll summarize for some others. One very important example, but speculative, is the thermal production of Wimp dark matter. In supersymmetric models, for example, there is a lightest superpartner. In memory models, it is a combination of gauge bosons called the Neutrino. And there's a lightest one, I'm just going to call it chi. And there are, of course, in the supersymmetric models, this Neutrino is typically a Majorana fermion. So two of them can annihilate. into many different products depending on the masses. So for example, if the neutrino is heavier than a Z, it will decay, it will annihilate into pairs of Z's. It can annihilate through various diagrams into pairs of photons, even though it's electrically neutral. E plus E minus pairs, etc. There are many, many processes depending on M-chi and, of course, uncouplings, which I won't go into, but later speakers discussing supersymmetric models will. Now, in chemical equilibrium, we have this relationship between the chemical potentials, and we also have the distribution, the phase space density, as a function of temperature and chemical potential. And the number distribution, let me back up here. For the neutralinos, which annihilate through some channel into pairs of photons, remember that photon number can change as a result of Bremsstrahlung. And when Bremsstrahlung is, electromagnetic Bremsstrahlung is in equilibrium, that ensures that the photon chemical potential is zero. And we see today in the microwave background that the photon chemical potential is very, very small, compared even with the present temperature of 2.725 K, let alone the temperature here of MEV or GeV. So that means that the chemical potentials of the neutralinos would be zero. Here, chi is its own antiparticle. So for a zero chemical potential, I have that the equilibrium number density as a function of temperature is just the spin degeneracy okay, so for a Majorana fermion, that would be the equilibrium density. And I'm going to write the limiting forms depending on whether the temperature is much greater or much less than the mass. Okay, so when the species is relativistic, its physical number density goes like T cubed, the same as for photons and for all relativistic species. So the abundance is high, comparable to that of photons. But when the temperature drops below the mass, the reaction is driven to lower abundance of the chi particles by annihilation because, of course, this reaction will, it's exothermic, it will give some energy on the right-hand side, and if the plasma is too cold, there will be very few photons, for example, that have enough energy, or positrons, enough energy when colliding to drive the reaction in the inverse direction. In fact, the numbers of such particles will be restricted to those in the tail of the distribution for photons or for E plus E minus pairs, the Wien tail, which is exponentially suppressed. That's why you get this exponential suppression. But while chemical equilibrium holds, I can write down a rate equation let me back up here. I'm going to write down the rate equation, and then I'll say, when does chemical equilibrium hold? This is actually more general than chemical equilibrium, as you will see. So I take the number in a co-moving volume, A cubed, so I take a volume which would contain a fixed number of particles, provided the particles are not being created or destroyed. But then I have a source, and because the interactions are binary, this would be the number density, let's say, for the chi particle, so I'll put a subscript chi. So I'm going to have a minus n sub chi squared, the binary interaction, times a cubed, because I have multiplied this equation by a cubed, the expansion factor cubed. And then I will have this sigma v cross-section, and in the present case, this will be a cross-section for annihilation. So this term represents the destruction the annihilation of the chi particle. But I also have reactions which go in the opposite direction. And to be very systematic, I should write down all the binary interactions for all the different particle species. That becomes extremely tedious. If those other particle species are in kinetic equilibrium, and if I know their chemical potentials, actually I don't even need to know their chemical potentials, do I? I think I do, but I'm going to assume that there's zero chemical potentials. Then I can just use the condition that in equilibrium, this n sub chi must equal the equilibrium number density. So this is kind of a phenomenological approach to writing down what the binary collisions, the equation the binary collisions must obey without having to look in detail at every single process for every different momentum state. So this is kind of a detailed balance argument being applied to the chemical production and destruction of my species.
Question.
Yes?
So is one half reflected here because it's I think this Reginala Cosmia, so this one half is directly one.
Am I missing a 1/2? I guess that depends on how I define the cross-section. So I can always absorb, I cannot introduce a factor of 1/2 in here because I want in equilibrium the number density to be driven towards the equilibrium value. But yeah, depending on how you define the cross-section, you could put factors in here, but I've just absorbed them into this rate. Are there other questions? Okay. So how does the Hubble rate come out of this? It comes out of this because when I expand this term, I get dn chi dt plus 3h n chi, of course, times a cubed on the right-hand side, but I can remove the a cubed on the left side, but I can remove it on the other side. By the way, one should check the units. I have density to the first power on the left-hand side, density squared on the right-hand side, but multiplied by sigma times v, so that is a rate. The units are correct. So this is where the Hubble rate comes in. Hubble rate compared with n sigma v, that's gamma, so there we have it. Okay? So in equilibrium, these terms on the right-hand side are much more important than the terms on the left-hand side, and the abundance is driven to the chemical equilibrium. But this equation also would describe departures from equilibrium that arise when sigma v is small. And so we're going to make a transition then to where the right-hand side is negligible, and the density just decreases as a to the minus 3. That's the freeze out. Okay. You will see these factors of 3 times h in all kinds of equations in cosmology that use co-moving coordinates. Okay, so let's draw that abundance, and I'm going to draw n chi times t cubed to scale the abundance to that of the abundant relativistic particles. And since the photon density goes like t cubed, I'll plot n chi versus n gamma versus temperature, and I'll put in the mass of the chi particle here. At high temperatures, there's some constant which depends on the ratio of spin degeneracies of the particles and so on. But then at low temperatures, I get driven, when I'm in chemical equilibrium, I get suppressed by this Boltzmann factor. Which really falls off very, very steeply. Maybe not quite this steeply, but pretty steeply. So this is the equilibrium chemical equilibrium curve here, and it's driven down by many, many orders of magnitude so that essentially the particles would completely annihilate and there would be no dark matter left today, except for the breaking of equilibrium. So when the density of the chi particles gets small enough so that typical chi particle will not find a partner to annihilate with in a Hubble time, or indeed in the rest of the age of the universe, this curve levels off from the solution of that equation like that. And this is the process of freeze out. And the abundance can be calculated just by integrating the Boltzmann equation. Sorry about that. Okay, this, it turns out, this leaves, of course, a relic Wimp abundance, which is very, very important in these thermal Wimp models, with sigma v of the weak scale. So taking the Fermi constant squared times the mass of the chi squared to give a typical scaling of this, with the mass of the chi in the range of tens to hundreds of GeV, let's say 100 GeV. This produces a relic Wimp abundance such that omega, let's say in this chi particle, is of order 1. So weak interactions coupling to the gauge bosons, the W and the Z, with this mass gives a characteristic residual density of order 1, tenth to 1. This has been called by some the Wimp miracle, because, of course, this is a very interesting mass scale for supersymmetric models. You might expect the lightest neutrino to have a mass below the SUSY breaking scale, but not much below. And so this is a very natural scale. This basic idea goes back at least, not in supersymmetry, but for general weakly interacting massive particles, Lee and Weinberg, 1977. So it is one of the attractive features of supersymmetric models or other weakly interacting massive particle models. Thermal production will produce typically, characteristically, an abundance that's cosmologically interesting for dark matter.
Yeah. So the miracle is that if you wanted omega chi to be 1, then the mass has to be 1.
Correct.
Okay.
So for a little homework exercise, it's easy for you to do. Ask yourself, how would this residual abundance depend on m chi? What happens if m chi is much higher or much lower? By the way, I have to say, give one key point here. This assumes that the decoupling occurs when the particles are non-relativistic. That's actually quite crucial. Again, an m chi there instead of a temperature squared. And another thing that follows, if the chi particle, when it decouples kinetically from the plasma, if it decouples kinetically, I've talked about only chemical decoupling here. If it decouples kinetically, which in fact happens around the same time, then the momentum distribution will be the non-relativistic Fermi-Dirac distribution at that time. And in fact, the +1 is not terribly important for the zero chemical potential and for the temperatures, the energies of relevance for a non-relativistic massive particle. That's why we get the e to the minus mt. Well, the chemical potential just gets absorbed into a prefactor on that. Well, in this case, there's no chemical potential, so forget what I said. But when the temperature is less than the mass, this exponential dominates over the 1. That means that you're going to get a non-relativistic Fermi-Dirac distribution, which is just a Maxwell-Boltzmann distribution. Non-relativistic Maxwell-Boltzmann. Okay. And you can calculate just by letting the WIMPs expand freely and follow how their momenta redshift. You could calculate the temperature of the WIMPs today if they were uniformly distributed, and that temperature is extremely cold. It's often in the range of nanokelvin or less. So this is actually a key thing that is a little different with neutrinos, as I will mention later on. The momenta redshift, that is to say, for a given chi particle, p is proportional to 1 over a of t. So when the particles are relativistic, the momenta are typically of order the mass. When they decouple, the momenta are of order the non-relativistic momentum of a particle whose thermal energy is kT, so that's much less than the mass. And then the momenta decrease by many, many orders of magnitude further as the universe expands, preserving the shape of the distribution function, which is non-relativistic Fermi-Dirac or Maxwell-Boltzmann. And so that means that the temperature of this chi particle is proportional to 1 over a of t as well. And as I said, typically this is 10 to the minus 9 Kelvin today for WIMP models, or less. So we're in a wonderful place, Gila, where the atomic physicists created the first Bose-Einstein condensation with atoms cooled down to microkelvin or nanokelvin temperatures. But the cosmic dark matter may even be colder than that. Yes?
But it's not in equilibrium, so it just has, so saying it has a temperature is really saying it has a Maxwell-Boltzmann distribution.
Correct.
With this parameter.
Correct. Here the temperature does not describe interactions. It only gives you the form of the momentum distribution. And that's really important. The similar effect will come up with neutrinos, as I'll mention in a few minutes. Yes?
So to what extent is this mass that you have there, is that model dependent? In other words, like,
Oh, sure.
what's sort of the range of masses that you can live with for various most common used models?
Well, I'm not a particle phenomenologist, but I know that there are variations of the minimal supersymmetric model. For example, there's a family of models called the constrained minimal supersymmetric model, which has a number of parameters in it. And you can tune those parameters to make the lightest neutralino mass range widely, probably from 10 GeV to close to a TeV. I'm sure you'll hear talks about that later in this workshop in the summer school. And typically what the particle phenomenologist will do is ask for the cosmological bounds, because they'd like to know, of course, not that the neutralino does not overproduce the dark matter. It could underproduce it because we may have more than one contributor to the cosmic dark matter. I'm only talking here about thermal relics and focusing on the WIMPs. But there's, for example, another class of dark matter particles whose production and interactions are extremely different, axions, which also could contribute to the cosmic dark matter. Yes?
Is there a relation between the temperature of neutralinos with the temperature of the CMB?
Oh, there is. I suppose you can write it down using the mass of the neutralino and the cross sections and so on. That actually is a good homework exercise. I suggest it to you. You can do that using the information that's on the board and in the previous lecture. Yeah. Yes?
For your expression for N sub EQ on the other blackboard,
Yes.
Are you assuming kinetic and chemical equilibrium? Or?
Yes. No. Well, yes, I'm assuming kinetic equilibrium, obviously, and chemical in the sense that I'm assuming zero chemical potential. So, absolutely right. Yes?
Just in that expression, that's minus over T.
Sorry, where did I make the mistake?
In the integral. Suppressed.
Really?
At large energies, it should be volts. E to the mod.
Oh, because it's in the, sorry, no.
I do make mistakes at the board, but so thanks for checking. Yes.
If it's P-wave annihilation, what's the typical dark matter mass?
If it's P-wave annihilation, what is the typical dark matter mass? That's still very model dependent, and I don't remember. I can't tell you, but others will, I'm sure, later. Okay, good. I'm glad that there's some interest in this subject. I hate to have to change gears. There's some beautiful stories about primordial nucleosynthesis and recombination. Maybe I'll just try to do them quickly just to give you the highlights. I guess the main lesson of this discussion of thermal processes is that elementary statistical mechanics can get you very far in cosmology without necessarily having to do complicated kinetic theory. Okay, we'll see how well the chalk works on a damp board here. So in brief, and you'll have the notes, which give a little bit more. Primordial nucleosynthesis is the production of the light elements through combinations of nucleons. So let's suppose this is at temperatures less than a few MeV, and actually you'll find the interesting thing, which you might not have expected, is that nucleosynthesis actually takes place at temperatures much less than a few MeV, and I'll explain why that's surprising in a moment. So neutrons and protons, of course, can bind together to form a deuteron, which has a binding energy. I'll call it B. Here I'm just only recalling from my nuclear physics, and I'm probably wrong, so will somebody correct me? Is it 2.2 MeV, the binding energy of the deuteron? Okay, good. I'm glad we have at least one nuclear physicist here. And the deuteron is an important catalyst, really, for the production of heavier nuclei. Deuterons will produce tritium or helium-3, and then tritium and helium-3 will go to helium-4 plus a nucleon. All these reactions are quite exothermic, meaning that they can happen at low temperatures, but the reverse reactions will not occur at low temperatures. The products don't have enough energy to reverse the reaction. So deuterium is the important step in producing helium to go to heavier nuclei with a mass number of 5 or higher. You need high temperatures because of Coulomb barriers for those products, for those reactions, and therefore they're endothermic. There's some endothermic reactions there where you just don't have enough energy in a plasma when it's cold. And so that's why Big Bang nucleosynthesis produces a lot of helium, but very little of the heavier elements. Now, naively, you would expect this first reaction would produce a significant amount of helium, or of deuterium. when the temperature is of order the binding energy. Well, that's quite naive because it takes a photon of energy 2.2 MeV to photodisintegrate deuterium, and you'd say, oh, well, all right, that means I need a temperature of about 2 MeV. However, there are 10 to the 9th photons for every nucleon, roughly. That is the important number, really, of the early universe. Baryogenesis leaves us with this enormous ratio of the number of photons to nucleons, and that's the baryogenesis issue. So even the photons in the tiny Wien tail, 10 to the minus 9 of the photons, not 10 to the minus 9 by number, but a tiny fraction of the photons can make the reaction go the other way to destroy deuterium. So this reaction remains in chemical equilibrium to quite low temperatures, much less than 2 MeV. Photodisintegration is important to temperatures of a few tens of keV, much, much less than an MeV. And so the reverse reaction remains in chemical equilibrium for quite a long time. And now we can look at the abundances using the chemical equilibrium discussion we had before. We have non-relativistic nuclei. The temperature is less than an MeV. The masses are much greater. So we can write down for each of these species, and I'll take species X, which could be neutron, proton, or deuteron. The formula now explicitly carrying along the chemical potential. So like we had for the neutrino, the +1 in the denominator, or -1, depending on whether it's fermion or boson, is unimportant because the exponential is so large compared with 1. And here we need to carry along the chemical potential. The chemical potential is basically just the logarithm of density divided by photon density with some powers of mass in here. Okay? So think of chemical potential as measuring the density, the relative density of these particles. This is in chemical equilibrium, and in chemical equilibrium we have that the sum of the chemical potentials on the left-hand and right-hand side are equal, and of course, again, chemical potential of the photon bath is 0. So it's very straightforward to combine NP and N and ND in such a way that you eliminate the chemical potentials using that relationship, and then you can write down in chemical equilibrium, for example, the ratio of the number density of deuterons to neutrons. And I have to take 3 of these N's, one for the protons, one for the neutrons, one for the deuteron, to eliminate the chemical potentials. But to make a dimensionless ratio, I need 2 pairs, so I'm going to introduce the photon number density as well. That's why I have this factor pi squared over 15. And NP over N gamma. So this is in chemical equilibrium. And now let's look at this. This factor NP over N gamma is of order 10 to the minus 9. This factor is also dimensionless, depends on the temperature, and I will evaluate it at about 60 keV, where it's 10 to the minus 6. So I have something that's of order 10 to the minus 15. multiplying an exponential. And you see that if the temperature were the binding energy, then I have an abundance of 10 to the minus 15. So you can take the logarithm of 10 to the 15th and solve for the temperature where the abundance ratio is about 1. And so this is about 1 when the temperature is about B over 40, which is about 60 keV. And that occurs almost 3 minutes after the Big Bang in the standard cosmology. It's closer to 170 seconds than 180 seconds. And time counts in this business because the clock is ticking, the temperature decreases, and you've got this exponential that quickly kicks in and basically converts all the neutrons into deuterium very fast. But then the deuterium gets converted into the heavier species very fast because these two are exothermic and the temperature is too low to drive the reverse reactions. So quickly, after 170 seconds or so, you end up turning the neutrons present at that time, pairs of them, into helium-4. Okay? So the question now becomes, how many neutrons are there? So to summarize this, all the neutrons, free neutrons, and I should say, preface by saying almost, all the free neutrons at T 170 seconds go into helium-4. So you'd think that the universe ought to be almost entirely helium-4 if this was very efficient, or if it was very inefficient, it should be mostly just hydrogen. Of course, the neutrons decay. I haven't even talked yet about the free neutron decay, which I will have to now. So what sets the number of neutrons at T of 170 seconds? And the answer is the freeze out of chemical interactions, freeze out of weak interactions. And the binary interactions are well known, just inverse beta processes. These are fast at T greater than about an MeV, maybe a couple of MeV. And so chemical equilibrium sets the neutron abundance at that time. And then there is a free neutron decay, which is slow. It has a rate, or an inverse rate, of 886 seconds, almost 15 minutes. Very slow compared with the 3 minutes during at which it takes the plasma to cool down for allowed deuterium to bind. And now in chemical equilibrium, which holds only above about an MeV in temperature for these reactions, e to the minus q over t, where q is the neutron-proton mass difference, 1.3 MeV. And just you can follow all the formulas we've been working with, the difference of chemical potentials here of nu E and of E and nu come in. At these temperatures, these chemical potentials are much smaller than the temperatures. The electrons and the neutrinos are not degenerate at an MeV. So this is 1. certainly for temperatures above an MeV. Those chemical potentials are negligible. So the neutron to proton mass ratio determines the abundance of neutrons as long as these reactions are in equilibrium. But when the temperature falls below about an MeV, they fall out of equilibrium. The weak interactions are not strong enough to drive this reaction. In fact, a similar thing is happening almost at the same time that the positrons are disappearing by annihilation. So this ratio freezes out at a temperature of about an MeV. And if you do a more careful Boltzmann kind of calculation, you find that this formula is reasonably accurate if you put in a freeze-out temperature of about 0.8 MeV. So the neutron-proton mass ratio is fixed at e to the minus 1.3 over 0.8 after freeze-out of the weak interactions. Then it gets suppressed a little bit by the radioactive decay, the beta decay of the neutrons. So for temperatures less than about an MeV, the neutron to proton mass ratio works out to be about 0.16 from this exponential times e to the minus gamma. Let me call this a gamma sub. Where did I write the gamma? Gamma sub d, for neutron decay, gamma sub d t. And that's enough to give the information that will produce the residual helium abundance. In fact, it's very easy. You take every pair of neutrons goes into helium-4. You can work out the math for yourself and find out that this turns out to be about 25% by mass fraction of helium. So it's pretty amazing how all this works. It depends on the baryon asymmetry, the photon to baryon number ratio. It depends on the mass differences of the nuclei. And for those reasons of particle physics and nuclear physics, the helium mass fraction produced in the Big Bang is really an interesting value. It's about a quarter. It's enough. Just think about it. If all the nucleons were converted into helium-4, we wouldn't be here because helium-4 is chemically quite inert. Of course, there could be no helium in the universe that would be still compatible with the formation of complex molecules and chemistry. But the fascinating thing is that if you ask how much helium is produced in stars by nuclear fusion after the Big Bang, it's much less than is produced during the Big Bang itself. Whereas all the elements heavier than helium, aside from a little bit of lithium, are produced from stellar nucleosynthesis processes. So yes, the question.
Does this also explain the symmetry between positron and electron?
No. I haven't talked about conserved particle numbers, so I haven't talked about baryon conservation or lepton conservation and how those relate. Later speakers will. That the residual electron abundance is, of course, extremely important. I'm assuming that the plasma is overall charge neutral, so that there are just as many electrons left today as needed to electrically neutralize the protons. Yeah, that's all.
So successful BDN constrains the baryon asymmetry very severely.
Absolutely. And not only baryon asymmetry, they also constrain the number of relativistic degrees of freedom in the plasma because that affects this T and it affects the amount of radioactive decay. So I said 170 seconds. That is for 3 flavors of light standard model neutrinos. If you put in 4 flavors or 5 flavors or 2 flavors, you will change the T, you will change the helium production. And in fact, the realization that primordial nucleosynthesis could constrain the number of neutrino flavors, light neutrino flavors, dates from around 1980. I think it may be Gungott, Schramm, and Tinsley. I know Dave Schramm was instrumental in that work and wrote a lot of papers about it. the particle physicists at the time were quite skeptical of the ideas of using cosmology to constrain particle physics in the early universe. But this was, I think, just shortly before the inflationary cosmology really turned the culture of the field on its head and made the early universe a playground for particle physics. But still, this is quite a very interesting factor, because people speculate about sterile neutrinos, for example, other flavors, other states that may be present in the early universe. They would contribute to G star. Therefore, they would change the time for a given temperature. And primordial nucleosynthesis is set by the temperature, mainly. So if you change the temperature-time relation by changing the number of light species in equilibrium, you're going to change the helium production, and that gives you constraints on particle models.
So related with that comment, is the result of cosmology of CMB that there are at least one extra relativistic degree of freedom? Is that in tension with this result? Or?
If it was abundant in the early universe, yes. Now, there is a lot of discussion about how strong the constraints are, because we don't actually observationally know very precisely the so-called primordial helium abundance. There are estimates that range from 22% by mass up to maybe 24 or 25%. And to narrow that down, astronomers look at more than just the helium abundance, because helium is not that sensitive to the details of primordial nucleosynthesis. It turns out that the residual deuterium, and the deuterium plus helium-3, is more sensitive to the number of degrees of freedom, or to the photon-to-baryon ratio. That's another factor that's used in constraining particle physics models. So the global fits for Big Bang nucleosynthesis use the residual deuterium and helium-3. They use the trace amounts of lithium produced in the Big Bang, which I haven't talked about. And the whole set of constraints suggests a best fit of about 23.5% or 24%. But that is in mild tension with some of the astrophysical measurements from stars. And it's really hard to know when you're looking at an old star. Was there helium production in the core? Is there separation of helium in the star? Helium is heavier than hydrogen. It might sink to the center. Convection can dredge up helium. It's a complicated astrophysics question. And so most practicing cosmologists will just take the kind of the best fit value that gives you about the right deuterium, and use the astrophysical constraints on deuterium as opposed to those on hydrogen or even on lithium. So it's a lot of complex astrophysics that I have to just gloss over. Are there other questions? Okay, well, these are really important things, and I haven't left much time for the rest, so I'm going to try to do what I think is most important here on the board and leave the rest to notes for the remaining time. I'm not going to be able to talk about hydrogen production in the late universe, which happens not at a temperature of 60 keV, but at a temperature of 0.3 electron volt. People call that recombination. Really should be called first combination of electrons and protons. The good news is that if you follow this story, the hydrogen production, a lot of it can just be copied back down. The same kinds of physical processes enter into hydrogen production, as you see from the notes. But I just wanted to mention a couple of things, very important processes for which I want to indicate results but not give derivations, at least to mention them. The weak interactions decoupled. And from the perspective of the neutrinos themselves, if I look at the rates of production and destruction of neutrinos as opposed to neutrons, Then, of course, I have three flavors of neutrinos, and all three flavors are important in the energy budget of the universe, but they decouple at slightly different temperatures. Because these temperatures are much less than the mass of the muon and the tau, the charge current interactions can go both ways for electron types, but not for muon and tau. Because the plasma just has negligible muons and tau at these temperatures. So the charge current interactions keep the electron neutrinos thermally and kinetically coupled to later times, slightly later times, lower temperatures. And when what happens, it's similar to the story we talked about of the Wimp decoupling, except one difference is that the neutrinos decouple when they are relativistic. So the decoupling temperature is much greater than the mass of the neutrino. We think the sum of the masses is less than about 2 electron volts from cosmological bounds. And that implies that the neutrino distribution function has somewhat different form. Now, I cannot ignore the plus 1. I can't ignore the plus 1 when the decoupling temperature is large. This is for T greater than T decoupling, of course. But the amazing thing, this is also true for T less than T decoupling if this neutrino temperature is T decoupling. It decreases with expansion, so divided by A of T. And this is because you take the shape of the distribution function at decoupling, and then after decoupling, the neutrinos don't scatter anymore, so they just travel along their geodesics. They move in free fall through the universe. And I showed you in the second lecture that for photons, their momenta, as measured by co-moving observers, decrease as 1 over A. In fact, it's pretty straightforward to show that for any particle, relativistic or not, the momenta redshift is 1 over A. And because the momenta go as A, let's see, the momenta redshift, so they go as 1 over A, then the temperature has to go as 1 over A as well, because the whole shape of the distribution function just gets preserved by free expansion. So it means that today, that is, anyway, ignoring the clustering of neutrinos into galaxies, if we just look at neutrinos uniformly distributed in the universe, their distribution function has this relativistic Fermi-Dirac form, even though the neutrinos today are non-relativistic. And in place of E, we have P. That's truly remarkable. A remarkable difference between neutrinos and WIMPs. Neutrinos decouple when they're relativistic, WIMPs decouple when they're non-relativistic. Another important process, which we talked about a little bit, but there's one extra ingredient I want to state on pair annihilation. Pair annihilation has a very important effect on the neutrino temperature relative to the photon temperature. The electrons and the photons remain in chemical equilibrium. And of course, when I say electrons, I mean positrons and electrons in chemical equilibrium. even after neutrinos decouple. And in fact, for quite a long time. So there's a nice trick you can use without having to go through all of the statistical mechanics, that for the electron photon plasma entropy is conserved. Basically, entropy is conserved when interactions are in equilibrium. Both the forward and the inverse reactions go at the same rate. You can use the first law with the heat exchange being TdS. And I will not go through the calculation, but the elementary cosmology books I mentioned do. They show that the heating increases the photon temperature compared with the neutrino temperature by a factor of 11/4 to the 1/3. I know it's a strange ratio. It depends on the number of species, relativistic species, in equilibrium before and after neutrinos decouple. 11 is 4 plus 7, and the 7 is related to the 7/8. You can find that in the textbooks. And this is very important for a couple of reasons. One is it tells us what the neutrino temperature would be today compared with that of photons. It's not 2.725 Kelvin. It's reduced by the reciprocal of that ratio. It's 1.95 Kelvin today. But the spectrum of those neutrinos is relativistic Fermi-Dirac. So the T is just a parameter in the distribution function. We would love to measure that cosmic neutrino background directly because it's about 100 neutrinos per flavor per cubic centimeter. And if we could measure them, we could check chemical potentials. We could potentially check theories of leptogenesis, baryogenesis. It's very hard to measure particles which interact weakly and only in their collisions transfer, Kelvin of energy, 10 to the minus 4 electron volts. So that's very, very tough, very challenging. Hasn't been done.
Sorry.
Yeah.
So I understand that relation holds between the temperatures only if the coupling of neutrinos happen before the annihilation of electrons and positrons.
Exactly right. This is true only if neutrino decoupling occurs before E plus E minus pair annihilation. There is a little bit of pair heating that takes place during this time interval when the temperature goes down from 3.6 to 2.3 MeV. So there's actually a slight difference in the neutrino temperatures for mu and tau and E. And if you want to do really precise cosmology, then you should include that slight effect in the calculation of G star and in the neutrino abundances. That's absolutely right.
Okay, so instead of counting this effect in the temperature, people count this effect in the relativistic, in the number of relativistic species, right?
Let me write that down. Well, let me write down the how it appears in the number of relativistic effective degrees of freedom. The neutrinos remain relativistic until much later in the universe, until the temperature falls down to a few electron volts, if that's the neutrino mass. Of course, that's a great question. What's the neutrino mass scale? Are neutrinos... we know that mass differences, the differences of the mass squareds, from neutrino oscillations, but we don't know the absolute neutrino mass scale. So that's where we'd love to be able to measure the cosmic neutrinos, among other things. But so this is for 2 for photons, and then we're below the electron mass, so the E plus E minus pairs have annihilated. the only abundant fermions, relativistic fermions, are the neutrinos, so we get a factor of 7/8, times 3 flavors, times nu bar, 2 states, neutrino states of left-handed neutrinos. And there's 4/11 to the power of 4/3, because remember, this gets multiplied by temperature to the 4th, and the ratio of neutrino to photon temperature is 4/11. This is in the standard model. This ratio is 3.36. You can change G star by changing 3 flavors to something else, or you can just put in parametrically G star to account for other light degrees of freedom that might be present in your cosmological model. And then take this in the Friedmann equation. It will change the time-temperature relation. And it will have an effect, therefore, on big bang nucleosynthesis, among other things, but that's a very important effect. Okay, I have just about used up my time, but I feel obligated to make a few remarks on Robertson-Walker spacetimes, because the following lectures, particular next week, will be talking about perturbations of Robertson-Walker models. And you might wonder, what's that got to do with anything I've said? I've taken a perspective on introductory cosmology which may be different from what many of you have studied before. It's typical to start out by writing the metric and to say that general relativity holds. We're going to solve geodesics in general relativity and focus on space-time geometry. That's unnecessary, and I would say even misleading for most physics in the early universe. It's misleading because it locks you into the mindset that you need to have a theory of gravity before you can calculate things. In fact, all you need for most of cosmology is local interactions and special relativity. That is all I have done. But others are going to corrupt you. So I want you to be prepared for their attempts to corrupt you. I say this as a reformed cosmologist, or perhaps I should say a reformed general relativist. So I know the dirty secrets of general relativists. They put way too much emphasis on curved space-time metrics. But there are a few things for which you need the metric. If you're going to describe anything that's not local, so if you want to know the evolution of density perturbations of wavelengths that may be comparable to or larger than the Hubble distance, special relativity won't get you there. If you want to be absolutely certain about the expansion law of the universe, I derived, in quotes, Friedmann by a Newtonian type argument. Special relativity and Newtonian physics will not get you there. And if you want to describe results of observations where photons or other messenger particles have traveled a significant fraction of the Hubble length, special relativity will not get you there. You need, in that case, a full space-time metric. But what you don't need for most things is a theory of gravity. Never confuse a curved space-time metric with general relativity. General relativity assumes a space-time metric. It assumes the existence of one, and then it proceeds to write down some differential equations that metric obeys. Who needs those differential equations if you have the metric? And the cosmological principle that I mentioned before at the beginning, that empirically and kind of philosophically, space-time seems to be a series of evolving spatially homogeneous 3 slices, then we can just say from that principle it must follow the space-time metric has the form of an evolving set of geometries which are spatially homogeneous. And this Robertson-Walker metric is a generalization of the Minkowski metric to an expanding spatially uniform space-time. I'll say space, because the expansion I'm going to write down just with space. And Jesse almost succeeded in converting me to the other sign metric yesterday. But I'll write it down in the, well, okay, there's a residual general relativist in me. This DL squared is a space called the Robertson-Walker space of an isotropic homogeneous space of constant curvature. There are many different coordinate systems, but the simplest one is the spherical coordinates. Two-sphere angular radius r of chi. And chi, sorry about the notation, it's not the neutralino. This is the radial distance or the radial coordinate in the Robertson-Walker space. And this function r of chi has three choices. It's chi if the spatial curvature is 0. It's 1 over the square root of k times the sine of square root of k chi if k is greater than 0. And it's the analytic continuation if k is negative. No Einstein equations, no general relativity, just the cosmological principle at work. K has units of inverse length squared. This may not be the form that you're used to seeing it, where it's sine chi. In that case, chi goes between 0 and pi for the closed model, positive curvature model. My chi here has units of length such that if k is less than or equal to 0, it has an infinite range. But if k is positive, it's bounded. This bounded geometry is called a three-sphere. This is, of course, flat Euclidean space. And the bottom one is called the three-hyperboloid of constant curvature. Observational cosmology suggests that we're very close to this top model. It's what we call the flat space-time. In fact, prediction of inflationary cosmology. So I'm just going to do one last thing to prepare you for the discussion of inflationary cosmology, which is one last coordinate transformation to put this in a form which will explain to you about horizons, because you're going to need them for inflation. Bear with me for about 3 extra minutes. By the way, I've told you what the range of the chi coordinate is. And I have to emphasize this is a model. We don't think that the Robertson-Walker space-time accurately describes our space-time on the very largest length scales. There are good reasons to think we live in a multiverse which doesn't look anything at all like Robertson-Walker when chi is trillions of light years or more, trillions of parsecs or more. But within a few gigaparsecs, the universe seems to fit this model quite well. But I haven't told you about the range of the t coordinate. And it's really important. When you write down a metric doesn't tell you everything. It doesn't tell you topology. It doesn't tell you the ranges of the coordinates. And you need to know, do you live in a Big Bang universe that has a equals 0 at some finite t in the past, or not? That's actually a very pressing question of cosmology, and I don't know the answer, though I suspect there are a number of people in the audience who are sure they do. So I have some problems in doing this integral because I don't know what to put in for the lower limit of the integral. Maybe I can put in 0, but what does 0 mean if the universe actually has infinite age? I don't know. All right, I'll be daring and put in 0. Does the integral converge? There are very interesting questions here, which are very different in an internal de Sitter space than they are in an internal inflating cosmology than they are in standard Robertson-Walker. But with this coordinate transformation, A has single sign, so this is a monotonic relation. T of tau is monotonic, so you can solve tau of t is monotonic. It can be inverted. You can solve for t of tau, plug it into A, and write A of tau. And then we have minus tau d tau squared plus d chi squared plus r squared of chi d omega squared. And you see right away from this that null geodesics, which travel to us along radial paths in the universe, have an extremely simple form. Tau 0, tau today, minus tau is equal to chi. That's the beauty of this form of the metric. Leaving aside the angular part, it's just conformal to Minkowski spacetime. And therefore, the null geodesics that reach us, if we put ourselves at the origin of coordinates, are just the Minkowski geodesics. Very, very simple. And that means if you want to know about things like event horizons or particle horizons, you make a space-time plot, pretend that this is Minkowski, and all you need to know is that co-moving observers have world lines that are constant chi. This goes back to my introduction of the co-moving coordinates by taking a physical distance and dividing it by A of t. I had this R0. Now, instead of calling it R0 in my local patch of cosmology where I applied special relativity, I'm calling that coordinate chi in my global coordinate system that covers a large range of space-time. So this might be us and them. And if you want to know, for example, is there a particle horizon? In the past, is there a distance beyond which we cannot see? Say that this is tau 0 today. What you do is you draw your past light cone. And well, okay, I've drawn it so that them is at the particle horizon if this is the Big Bang. But in an inflating universe, inflationary cosmology has A proportional to E to the HT, where H is constant during the period of inflation. That's exponential expansion, and it's a de Sitter phase. It's what happens if you have pure cosmological constant. If you do this integral with e to the minus ht, you find, well, first of all, there's now no bound on t. A never goes to 0 at any finite t in the past. So t can extend to minus infinity. And so can tau. So in that case, these light cones will intercept all world lines, and there is no particle horizon. That's how inflation solves the so-called horizon problem. That if you assume that there was no inflation, you would say that there's a them beyond which you cannot see. And it could be that if you look in opposite directions of the sky today at spots on the CMB, separated by the horizon diameter, those would have been out of causal contact in a matter plus radiation dominated universe, but not in an inflationary universe. That's the solution of the horizon problem by inflation. So this gives you what are called particle horizons. So if there is some tau min, but there could also be a tau max. If you have the universe now entering a cosmological constant dominated phase, now A of t goes like e to the ht in the future, this integral converges. There's a maximum tau. tau max. And let me just draw that one with a different color. And now we can ask an opposite question. We ask, as we approach this, well, we can ask the following way. As we approach this tau max, are there observers who can never send us information? So we move the past light cone up to this point, and for all of this portion of the world line, we can never see what's happening. That is called a future horizon. It's called an event horizon. So if there's a maximum tau, this gives us event horizons, which happen in a lambda-dominated universe. So conformal time is very useful for a lot of reasons. It shows you the horizon structure. It shows you it forces you to ask questions about causality, and it has this very nice feature that it's quite easy to write down algebraically an expression for the past light cone. So observational cosmologists will talk about the chi distance to a galaxy. Sometimes that's called the proper co-moving distance. It has many names. Sometimes it's called a proper distance, because it is a proper distance when A of t is 1 today. There's this R of chi, which is, of course, as I said, the angular, I hate to call it distance, it's an angular radius. And I won't give derivation because I've gone on too long, but I will write down a formula for what's called the luminosity distance that is used in supernova measurements. And it is A of tau, which is tau 0 minus chi, times R of chi. I want to make sure I have that A in the right place on the numerator. It should be. No, it's my mistake. It's on the denominator. Times 1 plus c. And here's, in fact, the redshift distance relation using the co-moving distance chi, but that is not what the astronomers plot because they cannot measure chi directly. They measure a luminosity distance because it turns out that this luminosity distance is equal to, luminosity flux is L over 4 pi decibel squared. That's the definition of luminosity distance decibel, and cosmologists measure flux. They assume they can calibrate a supernova or other standard candle to know what L is, so observationally they solve for decibel, and when you work through the Doppler shifting of photons, you end up with this factor of A of tau emitted, which is tau 0 minus chi along the past light cone. So it turns out that this formula is really important and underlies a lot of the complexity of those curves from the supernova distance redshift relation, the curvature of those curves, and the dependence on cosmic acceleration all comes from the shape of A of tau and the relation between chi and tau, or chi and redshift. So I'm going to stop here. We'll take a coffee break. There will be a copy of the lecture notes available for you after lunch, and then you'll be able to see some of the details that I had to skip. But thank you very much for your questions and for the time spent with you. I've enjoyed it.